All right, welcome everyone, and today we're going to have Ptacek of one of the co-founders of Matasano Security come here talk to us about hardware virtualization and the security aspects of virtualization. So please welcome Ptacek.
Hi everyone. I don't know if my mic's working well. Oh, good. It's the first time ever. So like he said, I'm here to talk about virtualization. Couple of caveats before I get started. The first is that I talk really, really fast. If you guys want to yelp or something like that if I'm talking too fast and being really unintelligible like I am right now, just do that. The second one is that I gave this talk with two other people at the Black Hat Security Conference this year in Vegas. And we had an hour and a half to give the talk, and I still ran over. And I have this irrational thought that it's bad form for me to give the same talk twice in two different venues. So real smartly, I added about 40% more content to this talk. There's no earthly way I'm getting through this talk, and I apologize to you guys in advance. Something else you're never supposed to do when you give a talk is apologize, but there I go. So I may get really, really fast at points and skip through. I'll put the slides online at some point later on. So with that said, I'm here today to talk about one of the more important arms races in computer security right now. Almost everything interesting that happens in computer security is an arms race of some sort. People writing exploits, people finding vulnerabilities in software versus the people trying to patch those vulnerabilities in software before it ships is an arms race. Virus writers versus antivirus is an arms race. There's an arms race right now happening over virtualization, and the question is whether or not virtualization is going to hurt the security of the computers that we deploy, or whether it's going to help the security of the computers that we deploy. And I'm going to talk about some of the implications and some of the research that we've done in this space, which was my introduction. I want to say something real quick. This is the product of a joint research project between my company, my friend Nate Lawson's company in California, and Symantec. Symantec's a really big, huge public company, and I did not take the time to get their PR approval before I gave this talk, so I struck their logo from my slides, but I'll tell you right now that more than a third of the work that we've done research-wise was Peter Ferry's work. Peter Ferry's a genius. He works for Symantec. I have now propped Symantec, and I can move on. Who am I? I am Ptacek. I am a security researcher. I break software for a living. I find vulnerabilities. People hire me and people like me and my company to go and look at software that gets deployed on networks and find ways that attackers can exploit that software to break into computers. We're also a product company. We're shipping a product right now, so I'm a software developer kind of by training. And I have a semester of college to me, which I'm just saying because I'm giving a talk at U of I. So I have a semester of political science at UIC. So you guys are all better educated than I am. So there are three interesting things that I want to talk to today about virtualization and the implications that virtualization has on security. The first of them is that enterprises, the people who deploy applications that hold all your credit card numbers and your mom's credit card numbers, and the reason why those credit card numbers are being sold out of stalls in Estonia, enterprises are relying increasingly on virtualization. And if people's data is going to be secure, we have to depend on virtualization and on hypervisors to be secure, in particular to prevent attackers from compromising one virtual machine and using it to get access to all the other virtual machines on the same hardware. We'll talk a little bit more about that. We also want to talk about the fact that attackers are looking to exploit virtualization technology for their own ends. In particular, what attackers have done so far is we've looked at ways for rootkits and malware and viruses to embed themselves in their own special purpose hypervisors. And it turns out that's a very realistic attack. It sounds like a ridiculously hard thing to implement, and it's actually a ridiculously simple thing to implement. The research project that we presented about at Black Hat this year was about detecting virtualized malware. Virtualized malware uses hypervisors, uses virtualization technology to stop detection software from finding the malware, to create 100% undetectable malware. And then our thesis is just that there's no such thing as 100% undetectable malware, and we're going to present a whole bunch of ways that anti-malware software can detect virtualized malware. And then finally, and it's unfortunate, there's no way I'm going to be able to get into any real depth on this topic, but another really interesting use of virtualization that I hope is clear after I'm done slogging through all these slides is that Virtualization is going to help people like me break DRM software. In particular, DRM software depends on stopping debuggers from attaching to computers to recover cryptographic secrets from iTunes to break the iTunes DRM, or from Windows Vista to break the HD DRM. We're going to be able to use virtualization to create stealth debuggers or stealth reversing tools that'll be able to do that with no chance or no realistic chance of the DRM systems from actually detecting and stopping that. So those are the three things that are on our minds right now about virtualization. So the first thing I want everybody to understand, especially if you haven't done any real time in IT at a large corporation right now, is 5 years from now, there's no chance that any new piece of software that's shipped shrink wrap, like a new web application, a new JTEE web application, something like that, no chance that stuff gets deployed on a native machine anymore. Everything is going to be virtualized. Virtualization is cheap and it's ridiculously effective. It allows enterprises to install a piece of software in one place, package it up with the machine and the known good operating system configuration, have it run all the time, let them checkpoint it, let them save it off to disk and reconstitute it later on, let them move it around the enterprise. It's too valuable. And our enterprise customers, what we see happening is that everything is being virtualized. We're shipping a product in 2 months. We're shipping it as a virtual machine, because why not? So the way we look at it is virtualization is going to be as core and as important a piece of technology as the operating system is today. So when we think about virtualization security, we have to assume that every critical application that's running inside of an enterprise or on the internet as a whole is relying on virtualization software to keep it secure. And the problem there is that the whole point of virtualization is that you buy one big iron server and you put 100 different virtual machines on it. And they don't share any relationship between each other. And the hypervisor, the virtualization software, is designed to prevent the software in the kernel of one virtual machine from compromising the kernels of other virtual machines. We're relying on that to be true. If it's not true, then you lose one virtual machine on a big iron server with 15 other virtual machines on it. All 15 machines have been taken down. That's a huge problem for security. That's a deal breaker for security. People would not deploy virtualized virtual machines for sensitive applications if that was the case. So we're looking into ways that problems with hypervisors and problems with the design of x86 virtualization will allow attacks like that to occur. So let's think real quick, I'm going to reuse this slide, about the life cycle of an attack. I'm going to talk about 2 different points in the life cycle of an attack, but this is really straightforward stuff, right? Attackers scan networks and look for vulnerable machines. They find applications that are vulnerable that they can send malicious web requests to, or malicious packets to, or whatever, to break in. They write exploits to do that. They invade machines using exploits once they've found the machines they're looking to attack. And then finally, once you have access to a machine, your job is to hide yourself on that virtual machine, or on that machine, so you can retain your access to the machine as long as possible. This is how everything works today. If you guys are familiar with Metasploit, for instance, this is all automated at this point, right? You break into a machine with a tool like Metasploit, and you upload a stub of some sort that runs on that machine that allows you permanent access to the operating system of that machine. You literally run your code through that machine at that point. And the job that a real attacker does is they want to take that stub, they want to take that piece of software, the backdoor, the Trojan horse that allows them permanent access to the machine, and make it impossible to detect, so that people can't run antivirus software, they can't run anti-malware software, or can't run tripwire over the binaries in the operating system, find the machine, know it's been compromised, report the vulnerability to their vendor, and scrub the malware off the machine. That's how it works today. Machines don't get patched. Machines get broken into routinely. But the world doesn't end because people can detect the fact that that's happened. And what we're going to get into a little bit later is the fact that virtualization causes problems when we try to detect and clean up after machines get broken into. So I'm getting right into the technical detail here. x86 has kind of been, the Intel platform has been kind of a classic problem for virtualization, although in the real world it's largely solved. There are 2 different ways that you can actually virtualize an x86 platform. The problem that you have is that x86 classically doesn't provide any facilities to catch the interface between the kernel and the hardware, to catch the MSRs, the INDs, and the OutBs, all the different things that the kernel, that the Ring 0 software running on a machine uses to talk to and program the hardware. x86 classically doesn't give you any way to stop people from using that maliciously. So that on a classic x86 platform, if you have Ring 0 access, if you can run code in the kernel, you have full access to the hardware, and nothing can be done to stop you at that point, because you have access to how memory is translated. You have access to the devices that are out there. All the code that's running on the machine is under your control. And so the first way that the x86, that we can virtualize x86 platforms is how VMware did it like about 10 years ago. It's kind of a clunky sounding, but works out really well in practice strategy. And what we do is we look at programs as collections of clusters of machine code instructions. We call those basic blocks. A basic block is a run of instructions that terminates in a jump. So think about programs as collections of basic blocks knitted together. And what VMware does is it looks at those basic blocks before it runs code, and it detects the basic blocks that have privileged instructions inside of them. This diagram does no justice whatsoever to how that actually works, but the concept is basically we can find the places in the code that we're running that actually exploit the interface between the kernel and the machine. And we can translate those so they do different things. So instead of actually executing the privileged instructions, they trap out to a hypervisor. So by dynamically translating binaries, x86, old style x86 virtualization software can provide via emulation the trap facilities that the x86 lacked to provide virtualization. The interesting thing about this is that VMware-style virtualization gives the hypervisor, the thing that's controlling all the virtual machines, gives the hypervisor full control over all the instructions that are running on the machine. The hypervisor literally chaperones every single basic block running on the machine. I like this from a security perspective because you can do all sorts of cool stuff looking at the assembly instructions, looking at the machine instructions before they run. But it exacts a performance penalty, and it's also really hard to write. You have to write the dynamic binary translation. You have to write the basic block cache that VMware retains so that you can not have to execute every single instruction mediated by VMware. It's a lot of work to do it this way. It's a little bit buggy, and it's kind of clunky and slow. Or at least that's what the Intel people have to say about that, because Intel recently released a hardware virtualization extension to the Intel platform called VTX. And VTX is really simple. VTX just provides the trap facility that x86 lacked before, so that when you execute a privileged instruction, a read MSR or a write MSR instruction, that would allow you to talk directly to the chipset or reprogram a device. You can now trap on those privileged instructions. So instead of translating all the code that runs and running everything chaperoned by the hypervisor, you can write your hypervisor the same way that hypervisors kind of always worked on PowerPC hardware, for instance, with LPARs, right, as trap handlers. So think about it as, classically we have the ring 3 for user land, the ring 0 for kernel. What VTX introduces is ring -1. A place lower than the operating system that can catch the things that the operating system is doing. So these are two different styles of virtualization. And when we talk about virtualized rootkits, this is what we're talking about. It's really easy to set up a virtualized rootkit using this style of virtualization. So the problem that we have now is normally when you break into a computer and you use an exploit of some sort to get access to the computer, the next thing you do after you break into the application is you go after the kernel. What you want to get is super user access to the machines. You get access to all the data for all the applications, for all the users on that machine. With a native machine, that's kind of where the game ends. Because as soon as you have full access to the kernel of the machine, there's nothing else to get at. But in a virtualized environment, that's obviously not true anymore, right? Because after the kernel of the machine that you've broken into, there's a hypervisor, and behind that hypervisor are 99 other really excellent virtual machines to go after. And again, enterprises are depending on the fact that you're not going to be able to get past that boundary, to get past the hypervisor itself. That the worst thing you can possibly do is take over the kernel, which is basically one application running on that machine. So the way security researchers find new vulnerabilities today is that we write fuzzers. And fuzzers are tools that generate random outputs or random inputs for the applications. They generate random URLs or random arguments to URLs or randomized packets with randomized fields, all sorts of malicious bad packets and requests and all that. And they use that to break into applications. You run it for an hour or a day or whatever, and you look at the logs of what you get. And as a result, you find a bunch of different vulnerabilities. And this technique, dates back to like maybe 2000. It's extremely effective. It's how most vulnerabilities get found today. Well, people thought to fuzz applications. We've been doing that since 2000 to find different application level vulnerabilities. And it was also pretty obvious to us that once we actually had vulnerabilities that would allow us access to userland, it would make a lot of sense to fuzz the userland to kernel interface as well, to find vulnerabilities in the I/O controls or in system calls, which also works really well and allows us to find kernel vulnerabilities that let us escalate privileges once we break into machines. What we didn't think a lot about was, once we had the kernel, should we fuzz all the different things inside of the kernel? Well, what would the point of that be? Because we already have the kernel. We already have full access to the machine. So it hasn't been until very recently that anybody actually thought about, well, maybe we should look at what happens inside of the kernel as well and find vulnerabilities in there. So what happened was, earlier this year, a really, really smart guy at Google named Tavis Ormandy wrote a paper, which I highly recommend, called, well, that. And what he basically did was he wrote a fuzzer that went after the kernel to device interface for different virtualized platforms. And what he found was that if you fuzz, say, the CSRs used by the NE2000 driver that QEMU and Xen provide you with when you're actually running. Obviously, when you run in Xen, you don't get the actual Ethernet driver that you'd normally be talking to. They give you an emulated fake Ethernet driver that you're actually talking to. So what he did was he basically fuzzed the interface there. And when he ran all sorts of random crap through the CSRs, all of this stuff, by the way, not real hardware, being executed by software. All software has bugs. So just an inevitable problem that we have with computers. All bugs can eventually be turned into security vulnerabilities. This is the way that security people look at this. So you run random inputs at something that's never been really tested, and you find vulnerabilities. And Tavis Ormandy found vulnerabilities. He found them in every mainstream virtualization platform out there. All these vulnerabilities that he found were exploitable. He found an integer overflow, which is one bottle of beer on the wall, one bottle of beer, take it down, 0 bottles of beer on the wall, 0 bottles of beer on the wall, take it down, 4 billion, 6 zillion, bottles of beer on the wall is the integer overflow. He found an integer overflow in the NE2000 driver for QEMU. He found an integer overflow in the power management subsystem that VMWare was emulating. And all these things would allow him to take over the hypervisor. And once he takes over the hypervisor, he has access to every guest operating system that's running on the same box. He hasn't published any of these exploits, which makes them more credible to me. He has a paper out there talking about how he found them. One thing you can do right now is go write fuzzers for CSRs. Not that hard. And you'll find vulnerabilities that allow you to break into different guest operating systems, and somebody will pay you $10,000 for each one of those that you find. There's markets for vulnerabilities now, and vulnerabilities cost money. Those are really useful vulnerabilities for people to have. They're worth lots of money. You can go find them. Even Xen, they found vulnerabilities. Xen isn't even fully virtualized. It works in tandem with the operating systems running on the machines. But Xen inherited a bunch of QEMU vulnerabilities that he found. So one way that hypervisors and virtualization fall to attackers is that attackers will look at code that hasn't been audited before because it was never in play. But now it is in play because it's part of the boundary between you and every other guest operating system on the platform. Another problem that we have, though, is just architectural. The problem is that one of the big issues that we have with virtualization and actually making it work is performance. The performance problem is primarily due to the fact that virtualization gets in between the kernel and the devices that the kernel wants to talk to. It's putting another layer of translation and of inspection and mediation between DMA calls or reprogramming devices calls and things like that, right? So it's getting in between the kernel and the devices, in particular the network devices, which are getting many, many packets per millisecond or whatever. So the strategy that virtualization vendors have to solve that problem is device affinity, which is just the idea that we're going to be able to take a virtual machine and give the virtual machine full access to a single device. That device will be tied to that virtual machine. And the way it looks like that the virtualization vendors looked at this from a security perspective was, we'll create a boundary that ties this device to this virtual machine so that no other guest on the same platform can talk to that device. So that virtual machine will own that device. And as long as that boundary is enforced by the hypervisor, we're all safe. But that's totally not true. The problem is that your Ethernet device isn't inside of the CPU. It's not bound by any of the restrictions that the CPU has. It's not bound by virtualization. It's not even bound by memory translation. So the simple attack here is that if you have device affinity set up, if you have a virtual machine, you break into it, it has direct access to an Ethernet driver, for instance. It's part of the device interface. It's part of the programming interface for the Ethernet card to be able to set up direct memory transfers. You give the device a physical memory address to write packets into. you can aim that anywhere inside of physical memory, untranslated, non-virtualized physical memory. And the attack is simple, right? You reprogram the device that the next 10 packets that come in go into the physical memory of a different virtual machine. And you write over the virtual machine. You have control over the memory of other virtual machines. Game over. This is an architectural problem with the platform, and it's going to be kind of a long-term source of vulnerabilities with x86 virtualization. Am I talking way too fast so far? Okay, good. There's no way that I'm going to get through this slide. But I'll post it somewhere. Again, I just want to make the point that you guys are probably familiar with the idea of the North Bridge and the South Bridge and the chipset versus the CPU. Pretty much everything that isn't in that far right column lives inside of the CPU. Virtualization lives inside of the CPU. Memory translation lives inside of the CPU. Your sound card, your network device doesn't live inside of the CPU. It's attached over a bus to the South Bridge, which contains the DMA controllers for the platform. Both the CPU and your devices talk via the chipset, via the North Bridge and the South Bridge, to a bank of DRAM somewhere. There's currently in the x86 platform no security in the chipset there. There's no protection between the sound card or the network device to stop the network card from having full access to physical memory. There's a technology that both Intel and AMD are introducing right now called IOMMU. It's a memory management interface that allows for virtual address translation for devices. And it gets integrated into the South Bridge. And now you can actually program the South Bridge so that a device can't access memory that you haven't allocated for it. There's a paper that just came out like a couple weeks ago where a bunch of researchers looked at the performance impact of actually using IOMMUs. And the long and the short of it is that for most of the ways that people were thinking about using IOMMUs, it's too slow. Every time you get, you have demand every time a packet comes in, requirements to actually change and reprogram the IOMMU, and you wind up pegging the CPU at like 70% or 80% of just programming the device that has to sit in between the untrusted Ethernet device and the rest of the chipset. So that's what we're working on right now in terms of x86 security, is trying to figure out a way to protect the devices from the rest of the platform and of physical memory. And I'm skipping this slide. And I'm getting into the Black Hat talk that we did after that really bad job of scene setting and talking about virtualized rootkits. Like I said before, we break into computers with exploits. We load some backdoor onto the machine that gives us permanent access. We try to hide that backdoor, which is where we are now. There's a long history of backdoors, of different technology used to hide backdoors on machines, dating all the way back into the 80s. Probably everyone here is familiar with the Thomson compiler backdoor, where you put a backdoor into the C compiler, and when you compile a binary, it inserts when you compile login, it reinserts the backdoor. When you compile the compiler, it puts the backdoor back into the compiler. Best example early on but it kind of progresses from there. It gets actually a lot more primitive and works its way back up there. We've had rootkits since the early 90s. Rootkits were originally tools that after you broke into a Sonos machine or a Solaris machine, you'd upload this package of .c files and compile them and replace the login program with a version of login that you specify that has a compiled end password that you would use. That's where it kind of starts. And it goes up from there. People, you backdoor the login process, you put a sniffer on the machine. You want to hide the fact that there's a sniffer on the machine right now. Otherwise, when somebody runs PS, they see a sniffer taking up all the memory there, and they know their machine's been broken into. So, we write backdoors that get in between PS and the kernel. So you can stop PS from dumping the processes and seeing the sniffer running there. That's a KVM rootkit. And then people say, okay, well, I'll program directly to the kernel and not use the libkvm interface to getting processes. And then so people come up with artificial ways of injecting kernel modules that can, inside of the kernel, prevent people from listing processes. If you see, this is obviously like a straightforward arms race. Every time we come up with a defense, somebody comes up with a way to negate the offense and the defense, and we move on. What we're seeing kind of jumping to where we are today is it's progressed to the point where attackers are using virtualization and firmware as a way of hiding rootkits and hiding malware. Actually, the firmware rootkits are a lot more interesting than the virtualized rootkits. I'm on the there's a battle running between the people writing virtualized rootkits saying virtualization technology gives us the chance of making fully invisible, fully undetectable rootkits, and people like me saying no, it doesn't, and here's how you would detect them. But independent of virtualized rootkits, there's also a notion of, well, there's all these different embedded processors and embedded memories inside of the chipset and inside of the operating environment of an x86 machine. For instance, your graphics card has what's called an op-ROM embedded into it, which you can program. And when the machine boots up, it's going to probe all the devices that are on the bus there and find devices that have op-ROMs that have initialization code for those devices. You can put backdoors in there. You can hide code in there that will run at boot time. That's not even in the DRAM of the machine. That's not persistent on disk, and it's not on DRAM. It's embedded in the memories of different devices that are plugged into the machine. Those are genuinely hard to detect. You have to have code for every single different type of device that plugs into the machine to stop that. Interesting, worth knowing about. I'm talking about virtualized rootkits. A concept I want to introduce with virtualized rootkits is hyperjacking. What a hyperjacker is it's a specific way of using virtualization extensions on a computer to hide a rootkit. It is not full virtualization. When you virtualize, when VMware runs on a machine, it has a whole bunch of different jobs that it has to do. It's basically scheduling different virtual machines, different kernels running on the same machine. It has to provide memory management, for instance. It has to provide scheduling capabilities so all the different virtual machines can actually run. People have this notion when they think about virtualized rootkits that what you're essentially doing is you're loading all of VMware into the machine, and that you have to load all that type of code in there, that you have to load a memory manager in there, you have to load a scheduler in there, that's about as big as VMware. And that's totally not true. Like I said before, this notion of Intel's trap and execute extensions for virtualization, what they basically do is they provide a ring -0, a trap handler. There's no reason that we have to actually use, or we have to write all the code that schedules different operating systems. What we essentially can do is load a VMM or load a hypervisor that runs alongside the kernel, not on top of or underneath the kernel, not scheduling the kernel, not providing memory management for the kernel, but simply another trap handler that runs when certain instructions on the machine run. That's essentially what a hyperjacker is. The idea is essentially that you use the VTX instructions on the machine to set up a hypervisor that runs in exactly the same memory space as the kernel. It takes very little code to do that. You just copy the segment registers from the kernel into your hypervisor so that your hypervisor is running in the same execution context as the kernel. The only difference between the hypervisor and the kernel is that the hypervisor runs at a slightly higher level of privilege, and you can transition directly to it from user land. So the real point here is that hyperjackers are very, very small. There's almost none of the job that VMware has to do needs to be done by a hyperjacker. You can think about actually this analogy isn't going to work for most of you because you're not security professionals or whatever, but when security professionals test web applications, what they do is they run proxies. They point their browser at a proxy, and the proxy is what, and they run all their requests to a web application through the proxy, and the proxy inserts attacks into that traffic. A hyperjacker works exactly the same way. It's a proxy that's running in between the kernel and the hardware that the attacker controls. The kernel's interface to the hardware is exactly the same as it was before. The actual stuff that's doing stuff inside the hardware is still the hardware. We're not taking over any of that. We're not emulating it. We're passing all of it through directly to the CPU. But where we want to take control of things, for instance, when you write a request to go look in the memory that our hypervisor lives in, we can catch those specific things and block them or return fake data or redirect them or whatever. So it's a proxy that allows us to pick and choose between the different requests that we want to deal with. And pretty much all we're going to look at is network traffic coming into the box so that we can run our back door and so we can talk to it from across the internet, and attempts to scan memory to find us. We do those two things. We set up everything else so that the requests are mirrored directly to the hardware, and presto, we have a virtualized rootkit that has no observable footprint on the system. This is an idea that one of my former partners, Dino Daizovi, came up with last year and presented at Black Hat. He called his Vitriol. It's a hyperjacking rootkit that runs on OS X. At exactly the same time, a Polish researcher named Joanna Rootkowska came up with a much more publicized and, to be honest, much better virtualized rootkit called Blue Pill that runs on Windows Vista. This is an idea from 2006. And Joanna's idea when she presented this was, Blue Pill, my virtualized rootkit that runs on the AMD virtualization extensions for Vista, is an undetectable rootkit. You can't write scanning software that's going to find Blue Pill, because if you try to scan memory that Blue Pill lives in, it's getting in between that request to scan the memory and the results of that request, and they can redirect them or return fake data. It's not possible to detect Blue Pill is the idea. And we wrote our own virtualized rootkit with the same idea. This is really cool. You know, it's a way to write a really hard to detect rootkit. And we looked at it and we thought, you know, if you guys really want to know how Vitriol works, hopefully I'll make it through this. There's no chance I'm going to get through this. So skipping that too. So we basically took Vitriol and we played with it and we looked at Joanna's blue pill rootkit. And we came to the conclusion pretty quickly that Joanna's rootkit was a lot cooler than our rootkit. For instance, one of the problems that we had once we had a virtualized rootkit running on the system was how do we talk to it? How do we use it to provide a backdoor that we can talk to over the internet, the machine, and take control of the machine? We didn't have a really good way of doing that. And Joanna came up with this really clever trick. What she does is she uses the Intel debug registers. And she sets debug breakpoints, virtualized, undetectable debug breakpoints on the IP stack. Or in the Ethernet drivers. And as packets come into the machine, she intercepts them and looks at them to see if they're command and control packets. And she runs her own entire IP stack. She just used LWIP, which is an open source, lightweight IP stack. She runs her own entire IP stack inside of her hypervisor rootkit. She even supports nested virtual machines so that you can run Blue Pill and have normal virtualization happen underneath it. So you can have multiple layers of virtualization. One of the obvious problems with virtualized rootkits and how detectable they are is, well, okay, you just turn on virtualization yourself, and you know, if you didn't implement nested virtualization, you won't be able to do it, and that's a dead giveaway that you're maliciously virtualized. She does all this stuff, and we didn't do any of it. And we're looking at this and like, A, this is really clever, and B, it's a lot of work that we don't want to do. So we took a different tack, and we basically looked at her claim that this is 100% undetectable malware, and we used our virtualized rootkit as a test bed for coming up with ways to detect it. The first thing I want to talk about is detecting normal software virtualization. This isn't what Blue Pill uses, but I should make it clear to you guys that VMware is trivial to detect for a bunch of reasons. I mean, when you run VMware and you're running virtualized Windows Vista or virtualized Windows XP, there are registry keys that get set that say that VMware is running, right? But put all that aside, and you have underlying fundamental problems that VMware has of being undetectable. For instance, there's an instruction called SIDT, which stores the IDTR, the contents of the register that has the interrupt descriptor table. You can run the SIDT instruction, and it'll store a real copy of your IDT in an actual register from userland code, and exposes the fact that if you're virtualized, you'll get different values than if you're not virtualized. Joanna wrote this rootkit called Blue Pill. She called SIDT the red pill. You can take the red pill to get out of your to tell that you're virtualized and escape the fact that you're virtualized. There's a bunch of other things that make VMware trivial to detect. Probably the easiest is the fact that timing is really hard to mask under VMware. VMware is a heavyweight kind of virtualized environment, and the timings of all sorts of different operations are way off. There are other virtualized platforms. If you're a Mac person, there's Parallels. Thing to know about Parallels is not only is it detectable, but it's crashable. There are all sorts of instruction sequences that'll take Parallels down. Parallels is not particularly secure. This is Peter Ferry's work once again. Detecting software virtualization is pretty straightforward. It's pretty easy. Peter Ferry wrote a really cool paper, which I don't have any URL for in here whatsoever, but you can look it up online. Just look for his name. It's his best-known paper, of all sorts of different ways to detect the fact that software virtualization is running, finding errata, conditions that never happen in normal code, but if you go look for them, happen all the time. That'll expose the fact that VMware is running. But kind of intuitively, it's straightforward to think that VMware would be detectable because VMware goes through no effort whatsoever to not be detectable, and also it's big and heavyweight, right? Hyperjackers are not big and heavyweight. Vitriol is like 500 lines of actual real code. Hyperjackers are designed to be lightweight and small and hard to detect. So what we're basically doing is we're trying to find ways that the VTX hardware virtualization instructions themselves are detectable. And the problem that we come up with is what we call cross-section. And it's just the fact that if you as a piece of detection software are trying to detect whether or not you're virtualized or talking natively to the hardware. If you're talking natively to the hardware, then you know you can detect any rootkit that's running on the system because you can scan authentic memory and do it the same way antivirus does and look for malicious instructions in memory. So if you know that you're not virtualized, you know that you can trust your attempts to read memory, and you know that you can trust your attempts to find malware. If you are virtualized, then all you have to know is, am I supposed to be virtualized right now? And if I'm supposed to be virtualized right now, it's fine. And if I'm not supposed to be virtualized right now, that's a real problem. And so the primary goal that software that tries to detect virtualized rootkits has is trying to find out whether it's unexpectedly been virtualized. And the problem with this is that as soon as you can talk directly to hardware, it's game over for that. There's a million different ways that you can use to find out whether or not you've been virtualized. So when we look at the hardware, virtualized rootkits have this job of getting in between every possible request that Ring 0 software has to the hardware and detecting or figuring out the ones that will expose the fact that it's been virtualized. So you have this 500-line piece of code that is Vitriol or that is Blue Pill, and it does almost no device emulation whatsoever right now. It doesn't get in between you and the video driver. It doesn't get in between you and the network driver. The whole point of this software is that it's lightweight, that the real network driver is what's doing the network driver stuff. You're not even supposed to know that you're virtualized. Well, if you can talk directly to the network driver, you can use the network driver to scan memory. If you can talk directly to the video hardware, you can use the video hardware to scan memory or to write into memory or to do all sorts of things like that. So what we have to do is we have to start emulating a bunch of things that we didn't expect to have to start emulating before. And what was a 500-line piece of code becomes a 200,000-line piece of code that's no longer feasible to install. That's the cross-section problem. And I keep talking about the next slide that I'm going to give before I get to the next slide. But there's a deeper problem, which is timing. So once virtualization is turned on the x86 hardware, all sorts of things change in the system. They're not things that are directly evident in the programming interface, but they're things that if you know to look for them, they change. For instance, when VTX is turned on, when you issue the CPU ID instruction that tells you what kind of CPU you're working with and gives you all the characteristics of the CPU and its identifier and all that, that's normally a hardware instruction. It normally takes 200 cycles. It's just talking to the chipset and returning a value back to you. But CPU ID under VTX has to be virtualized. There's a bit inside of the return value from CPU ID that tells you whether you're virtualized, right? So if it wasn't virtualized, you could just use that bit to know if you were virtualized. But in VTX, you have to virtualize CPU ID. So now you have an instruction that used to take 200 cycles, but now actually hits memory. It has to execute a bunch of instructions and change a bunch of things in the platform. So just by itself, if all you're doing with CPU ID is handling it in your hypervisor in the simplest possible way, you go from 200 cycles for an operation to 5,000 cycles for an operation. It's pretty obvious how you can use that to detect whether you're virtualized. You just write a tight loop around CPU ID, and you look at the timing. And you see whether or not it takes a really, really long time to execute CPU ID. And if it does, you're virtualized. And if you didn't expect to be virtualized, you're unexpectedly virtualized. And red flag, something's wrong with the box. So we have 3 different strategies for exploiting these problems to detect virtualization. The first is what we call side channel attacks. Side channel attacks are cases where virtualization changes the performance characteristics of the platform. Basically what happens is when you trap out to the hypervisor, it changes things in caches, or it changes the execution state of the machine in observable ways. And I'll talk a little bit more about that in a second. The second class of attacks are vantage point attacks. So again, Joanna and Dino's thesis is we can write rootkits that will do almost no work, that won't intercept hardware, that won't have to emulate the device drivers, and just leave the machine talking to the real hardware, except when people attempt to scan memory for malicious software. Except for the fact that if you can talk directly to the hardware, if you can talk directly to your network card, you can use that to go and look in memory for evidence of virtualization, evidence of malware. So vantage point attacks are cases where the rootkit doesn't think to emulate things that need to be emulated to hide the rootkit that's installed in the machine. And the third class of attacks are just vulnerabilities in Blue Pill or Vitriol itself. There are a million things that Vitriol doesn't do properly. For instance, Vitriol will crash on this machine right now because it doesn't handle 64-bit emulation mode properly. There's all sorts of problems with both Blue Pill and Vitriol if you look at them carefully, where you can put a machine, if you're in kernel mode, you can put a machine into a state where it will crash. So you're also banking on the fact that Vitriol or Blue Pill is coded perfectly. And all code has bugs. And bugs in Blue Pill will betray the fact that Blue Pill is actually running. So the first class of attacks are side channel or timing attacks. I don't want to spend a whole lot of time on side channel attacks, except to say that timing attacks are kind of invented as a way of breaking cryptography. Paul Kocher kind of came out as probably the grandfather of timing attacks versus real modern cryptography. The simplest example of a side channel attack is just that you run a string compare between two things, a shorter string and a longer string. You can try short strings and gradually increase the size of your string, kind of guess when you get the right the right password or the wrong password with individual trials of individual bytes. So all you have to do is guess, the 26 possible characters, the 256 possible characters of the first byte of the password, and the timing will change when you get the right one. So you do the second one, the timing changes when you get the right second one. It's a pretty straightforward attack. That actually existed on 10x. That was an actual vulnerability. It occurs in modern cryptography in kind of the same form in really bad other systems that we've looked at. But you can use the same kind of general idea with modern cryptography, for instance, with data-dependent timings and RSA. Depending on the inputs that you give to a crypto algorithm, if it's not written really, really carefully not to betray timing, based on different inputs and different key values, you'll get different timing for the crypto operations. And Paul Kocher used that to break RSA back in '95. And Dan Bona took that same attack and used it against SSL. In 2001. He was able to do it remotely over the internet, looking at just different timings for different packets and collecting guesses about individual key bits. Paul Kocher's company, Cryptography Research, came up with a technique called DPA, which uses not only timing but power consumption and correlates the two of them statistically, and is able to break pretty much every smart card implementation that doesn't have their patented technology. Recently, a bunch of guys named Tromer and Aximez from Intel and a bunch of other ones came up with the fact that on modern CPUs, branch prediction, which is critical for pipelining, right? The performance of modern CPUs depends on things like branch prediction. Branch prediction is implemented with caches. So based on different inputs, a crypto operation will take different amounts of time based on whether different branches are taken. And you can scrub and probe the branch caches there to predict key bits. So the real point I want to make here is that timing attacks have been really effective against hardened software that's been designed not to betray timing and designed not to betray information. Cryptography, right? All we're saying is that you can use the exact same ideas to go after virtualization, to detect the fact that virtualization is running the platform. And most of the different timing attacks that have been deployed against cryptography work kind of as is against virtualization if you know where to look. One of the arguments that we've heard about using timing attacks against virtualization is that on a real system with all these different applications running, there's just too much noise to measure. You're looking at microsecond granularity or millisecond granularity events. And it's totally not true, right? The basic problem that the basic way you address the fact that you have noise on a system is that the noise will cancel itself out over lots and lots of measurements. Cryptographers or cryptanalysts have the exact same problem when they go after real crypto. You can extract RSA keys remotely from SSL servers over all the noise of the internet just by taking enough measurements. If you're on localhost, it takes way fewer measurements to do the exact same thing to detect virtualization. And it's also extremely hard to get rid of all the data-dependent paths. For instance, to eliminate branch prediction as a way of the branch prediction cache, right? You have to write code that is not data-dependent, that will not use the branch prediction caches, for instance. When our software runs to detect virtualization on the platform, we're at ring zero. We monopolize the entire system. So if we wanted to, and we don't have to, but if we wanted to, we can also just turn off all the noise for a couple microseconds while our detection stuff runs so that we're not competing with other applications running on the same system. That's a totally reasonable, realistic thing to do. If you've ever run Norton antivirus on a system, right, it takes the whole system down with it for like 10 minutes while it scans the hard drive. We're talking about 10 microseconds to scan memory or detect the fact that we're virtualized. So, just different ways to find side channel attacks. I'm going to skip this because I'm going to actually give you a specific example of a side channel attack that works against Vitriol and Blue Pill. So vantage point attacks, places where Blue Pill doesn't emulate a piece of hardware that allows the request to pass through directly to hardware so they can keep the code base down, and doesn't do that. Well, the problem again is that if you can talk directly to hardware, the hardware will betray the fact that virtualization is enabled, that you're virtualized. The simplest thing is you can do a lot of things to try and prevent people from timing individual instructions that trap out, right? So for instance, when you want to time the CPU ID instruction, if you want a high performance timer under x86, the normal answer to that is to use the TSC. There's an instruction called RDTSC, which returns a 64-bit cycle count. And that's what you use to time almost everything on the x86 platform. Well, the VTX designers, the AMD SVM designers, even VMware thought of that, right? So you can offset the TSC instructions. You can offset the read and timestamp counter instruction and fake out the timing there. So you would have control over what software thinks the timing is, right? But if you don't get in between the kernel and the devices, there's a million other timers running on the same machine. For instance, there's the HPET timer, the high-performance chipset timers that you can use to do the exact same thing. If you don't think to actually catch attempts to reprogram the HPET timers, you have an independent timing source that you can use to time the CPU ID instruction to see if you're trapping out, and then you know if you're virtualized. There are the performance event counters, which will tell you every time you have a cache miss. So for instance, if the CPU ID instruction winds up executing code instead of talking to the hardware, that code will change the instruction TLBs, will change the iCache. And that'll be measurable. You'll get, in a tight loop, you'll get a different profile of cache misses. And then there are all sorts of funky things inside of the chipset and inside of the CPU, like the x86 GART, which is what the graphics chipset uses to get coherent access to big blocks of memory. It's its own memory translation subsystem that runs specifically for the graphics, the graphics subsystem for AGP. If you can talk directly to the GART, if you can reprogram the... My phone's about to ring. If you can talk directly to the GART, you can use that to use the GART to sweep memory and scan for things. So you have to catch all the different places in the hardware where a rootkit might not think to trap that. A bunch of different things to look for with MSRs, with Vantage point attacks. You look for all the embedded hardware on the system. Blue Pill's not emulating any of it. And you look for all the different MSRs and CSRs, the control registers. These are the equivalent of hardware ioctals, right? They work exactly the same way. They're special registers that you read to or write from. They're mapped into memory. You write a value there, and something changes. You look for all the different MSRs, and you look for ways that they'll change based on timing or based on, or will change the way the device actually accesses memory. Or you look at devices and the way they talk to memory directly. You can set up DMA accesses and things like that as well. It's interesting, when you look at the x86 documentation, there's a whole bunch of MSRs that aren't even documented. You have to go look for and kind of black box reverse engineer what they do. So it's not even possible for you to look at a guide or a spec sheet and know what Blue Pill would have to emulate. They'd have to go through all the trouble of reverse engineering a bunch of details about the hardware that they're running on. It also changes with each different piece of hardware that you deploy. Two different machines with two different chipsets will have a different set of MSRs and a different set of CSRs, which if you don't know about and don't compensate for, you can use to detect virtualization. So I want to talk about, and I'm going to wrap this up on this one thing, which detects Blue Pill. And then we'll kind of wrap it up, and I'll take whatever questions I'm left with right now. So one simple side channel attack that successfully detects Blue Pill is the TLB. Like I said before, like the CPU ID instruction when it runs, when you're virtualized, traps out to code that has to access memory. It has to run itself, right, which means that the actual fetch of the instructions accesses memory, changes the iCache and things like that, right? And one of the things that it will change when it runs, one of the things that will change is that as that code runs, it'll affect the TLBs. The TLBs are special caches that run in the machine that assist in memory translation. So on the x86 platform, all of the memory mappings for different processes are stored themselves in DRAM. And DRAM is really, really slow. You guys are all familiar with the memory hierarchy here, registers and cache, and then normal memory, and then the disk. And the job of a system designer is to make sure that processes don't actually have to touch real memory, because real memory is really, really slow. So most of those memory translations are cached in a finite-sized fixed cache called the TLB. And one of the things that we can exploit is that when the CPU ID instruction traps out to a hypervisor, instead of actually running off the hardware directly, it'll influence what's actually in the TLB. So what we can basically do is we can write a sequence of instructions that will basically poison the TLB or set up a known value for the TLB and execute the CPU ID instruction. And what should happen is that should behave exactly the same way a NOP instruction would, because the CPU ID instruction doesn't normally touch memory. It has no normal influence on the TLBs or on the caches. And we can look for the fact that the TLBs, the timings, are different after our instruction sequence runs. If we're virtualized, we'll get a different value than if we're not virtualized. So what we essentially do is we start out in a situation where the TLBs have essentially random values in them, or whatever the normal memory maps were. And what we can do is we can directly write to the page table entries and set them up so they point to specific locations in memory, but not update the hardware until that the mapping has changed. And we can use that to run. I'm totally bombing on this right now because I'm running out of time. But we can essentially run a loop where we set up the TLB in a specific condition, and we run the CPU ID instruction. And after the CPU ID instruction runs, when we read from an address in memory, we'll actually get a different value out of memory because the memory mapping was changed out from under it, and it gets flushed to the TLB as a result of that. So what we do is we write a loop that runs CPU ID, and then afterwards we will sweep through a block of memory that we had predictable values in, and if a TLB entry changed as a result of code running inside of a hypervisor, we'll get a different value that pops right out of memory at us. And then I just explained what that does. Another interesting thing is that instructions themselves have their own TLB. So anything that you would do to defeat the data TLB to, for instance, attempt to not touch memory, well, the instruction fetches themselves change a different TLB. There are other caches as well. Like I said, there's a branch target buffer, right? So when code runs, anytime it branches, it changes stuff inside of the BTB, right? Well, you can pre-populate the BTB with specific values, run the CPU ID instruction, and see if the BTB timings change afterwards. You can run a tight loop of code in a different process that goes and constantly sweeps timings of different branches at different offsets. And if those timings change, you have evidence that the BTB changed. You can do that in a loop in ring 0 and detect the fact that virtualization is enabled. Another thing, I already mentioned the HPET attacks, the fact that we can go and use the HPET timers directly. So even if you try and offset the TSC, you can use the HPET timers directly to time code. There's a bunch of other timers in the in the hardware as well. There's the programmable interrupt timer, which is the classic slow timer. There's the real-time counter. These are devices that you have to actually program. And if you're not emulating those devices, then the virtualized rootkit gives itself away by the fact that those timers are returning true time for things that are, shouldn't have different timing based on whether or not you're virtualized. There's the LAPIC. ACPI has its own timer. And if you look inside of the different devices that are attached to an x86 CPU, all of them have their own timers built into them. Your wireless chipset strobes packets onto the wireless. It has a timer. You can look at the packets that are coming out of it and obtain timing from that. There's the VGA blanking interval. You can look at that and see how many times there's all sorts of timers that are embedded into devices that we can look at as well, again, to get different time sources. All of these time sources have to match up properly for virtualized rootkits to work. And then finally, you can fuzz the blue pill or vitriol directly. One of the best ways to do that is that blue pill actually implements nested virtualization. So it has to support the entire VMCS instruction set. In fact, it has to actually, or the entire VTX instruction set. It has to emulate those instructions, which means that we can write code that throws random values inside of the different data structures that AMD or Intel virtualization require to run. And we can use that to find bugs inside of blue pill and certainly inside of vitriol. The simplest way to find bugs in that code is to fuzz directly the VTX extensions. So our conclusion is that that virtualized rootkits are no harder to detect than normal malware. You have the exact same cat and mouse game between detection technology and malware authors that we had with antivirus. So sorry about the last part of that talk there. And I'm just looking at this clock here, and you guys all have to get to dinner. And so in the 3 minutes that we have remaining, does anybody have questions? Yes?
So what effect do you think some of the trusted platform module or Intel Legrand technology would have on detection? Would it make it easier, or?
That's a great question. So the question was, what effect will Intel Legrand or Intel TXT have on this particular cat and mouse game? I think that Joanna Rutkowska and our team agree that what TXT really does for this, what TXT does is it gives you a trusted boot path. Cryptographically assured, you know the software that's running on your machine. As long as there aren't vulnerabilities in any of those pieces of software, you know what's actually running on the machine. You also can't backdoor images that are stored on the hard drive, because when they load up, the crypto checksums will change. And that's actually enforced in a piece of hardware that's in the chipset. What it really does is by preventing persistent rootkits from running on the machine and by controlling access to virtualization, it makes it hard to install virtualized rootkits in the first place. So it's kind of a game over problem for that.
So the other part of it is that there's the new technology called dynamic rooted trust measurement, where you can launch a measured VMM. So do you think the rootkit is really a problem if you use a measured VMM?
Ask the question again. I didn't understand what you were.
So there's a new technology in the Intel chips.
I'm familiar with the dynamic measured VMM.
Right. So because you have a dynamic measured VMM, do you really care that you have a rootkit?
So, yeah, so the issue here is that if virtualization is already running, if you break a kernel that's running inside of a properly virtualized environment, the simplest thing that the virtualized environment can do to stop rootkits from having a real effect on the hardware is to prevent virtualization from happening at all. So if you have a trusted hypervisor already running, the thing that Joanna is exploiting here is the fact that virtualization isn't already set up. Think of it the same way that you think of protected memory, right? If protected memory was an option that was enabled on computers, protected memory would be a huge security problem, right? Because machines that didn't normally run with protected memory on, you could use the MMU to actually hide rootkits, to redirect memory access and all that. And if you didn't expect memory accesses to be translated, that would be a big problem for you. But it's not a big problem because everybody runs on machines with the MMU actually enabled and with protected mode enabled, right? Virtualization, the exact same thing. And that's how Intel, I think, looks at this, right? Is they think, well, in 5 years from now, VTX will always be turned on. The only way you can actually install a virtualized rootkit is to compromise the hypervisor in the first place. All the hypervisor has to do is not allow the VTX instructions to run. And they can prevent hypervisors from being installed. So I think virtualized rootkits in general depend on this notion that machines aren't going to be virtualized. They're exploiting that lack as a way of hiding the rootkit in a feature that wasn't supposed to be enabled. So the simplest answer is that you just turn off virtualization.
You mentioned how you could use memory coloring and the cache lookup table to find out, to verify states. About how much time are you actually taking to do your setup, the test, and the outflow and the processing?
I should have a good answer for how long it takes us to take the entire size of the TLB and desync all the TLB entries, and then run a loop around CPU ID, and then detect whether or not any of our desynchronized TLB entries, a process which I did a horrible job of explaining in this talk right now, how long that actually takes. I don't have a good answer for how long it takes, except that it takes less than user time, right? It's not noticeable. I should profile it, but the reality is that normal anti-malware software takes hyper user time, right? It takes ridiculous amounts of time. So we're way under the bar. It's a good question. I have a hard time thinking of a scenario in which the performance of the individual virtualized probes are going to be a big deal compared to the access to disk that has to happen for other things. It's obviously always going to be faster than disk access, which is what normal anti-malware software involves right now. But there was a challenge that we ran before our Black Hat talk where we said, well, look, Joanna, you give us access to Blue Pill, and we'll try to detect it. And if we can't detect Blue Pill, we'll give you the laptop. Sorry. We basically said, we'll take 2 MacBooks or we'll take 2 laptops, and you can install Blue Pill on one of them. And if we can't tell you which one you installed it on, we'll give you both laptops. That's no less distracting than it was in my pocket. And for a variety of reasons, it was deemed that would not be a fair challenge. And as it turns out, we can detect Blue Pill trivially because it doesn't do almost any of the stuff that we talked about, which is fair enough. It's a research prototype, and that's the argument for it. And she did a better job of coding than we did, so I'm not saying anything negative about her. But one of the stipulations for the challenge that she came up with was, first of all, we wait 6 months. And during that 6 months, we pay for her billable time to make Blue Pill hard for us to detect, which seems like a really bad deal for us. But then one of the stipulations was she gave us a finite amount of time that we could run things in because she didn't want the detector to disrupt the normal user's experience of the machine, which we thought was kind of a silly concern given what Norton antivirus takes anyways. But at the same time, we're way, way faster than what that stipulation was. We're way less than a second of running time to do that. I mean, we're talking about thousands of cycles here, not even millions of cycles to do that. That's not true, but we're talking about thousands of instructions, not millions of instructions.
To sort of follow up with the previous question, you mentioned then, I guess, that these TPMs and trusted boots and whatnot seem to be a good solution for this. But don't you, even with the dynamic root of trust, you still sort of have a time of check, time of use problem, right? Where, you still have. I mean, it narrows the window, but it's still a possible problem, right? Where if your hypervisor were to get compromised.
What you're basically saying is that if there's a bug on the hypervisor,
right.
it's true. I mean, if you have a bug in the trusted hypervisor that's running there, you have access to whatever code is running inside of the hypervisor, and you can use that to load a virtualized rootkit. You're essentially in the same scenario as you are now once that happens, right? It's a good point. I don't have a response to it, right? There's the hypervisor, even if it's measured dynamically, still has a code footprint that has an attack surface that we can attack and look at and find vulnerabilities in it. And nothing really changes about that except for the fact that we can't make them persistent. So as soon as the machine reboots, or if there's another hypervisor or another VM running on the same machine that's itself measured, doesn't have a vulnerability, and it's checking the machine, those things can be used to detect the fact that the rootkit is installed there. So again, we think that the game changes once virtualization is kind of a normal feature and installed everywhere, because a normal hypervisor isn't going to allow virtualization instructions to run in the first place, and a security VM, which is I think what Intel wants to see happen, is there's going to be VMs on the machine specifically running to secure the rest of the machine, would have a much smaller footprint and could be easier to audit. But it's a totally bad answer to your question of, I mean, if there's a hypervisor bug, you have control over the hypervisor, and